Welcome to quantum splitting. This is a pretty crazy one, so if you've picked this one out of the list, you might want to stay for the lecture. It's really fun and strange. So this is Physics X, Extraordinary Concepts in Physics. I'm Robert Nemiroff, who's teaching this in the beautiful downtown studios of Michigan Technological University. There are students taking this class, but you can, if you can discern this web address here, right there, you can make it stay. You can see all the lectures of this class. So let's get started here. First, I need to define a common thing that's going to be occurring in the next two lectures, a beam splitter. So let's say you have light that comes in here, and here is your beam splitter here, which is like essentially a half-silvered mirror that runs like that. So when that happens, two things can happen to your photon. It can come out here, or it could come out here. And if you tune it just right, and it might be tuned by the energy or wavelength of the photon, you can get it so that 50% of the time it comes down here, and 50% of the time it just continues straight. So these are pretty interesting. One of the reasons why it's so interesting is because these paths, these separate paths, can actually interfere. So it's a little bit like creating a two-slit experiment. The beam splitter, you can have photons that can go through the beam splitter and be reflected by the beam splitter, both. Same photon. Or can you? Let's go to the quizzing. Suppose a light is directed toward a beam splitter, so that light can take either of two paths around the rectangle. Okay, so what rectangle is there? So here we go. Light comes in here, and here's a beam splitter. BS means beam splitter, got it? So then light can go here. I should wiggle it to be a photon. Or it can go up here, where it's going to hit a regular mirror. Okay, so then light bounces and comes like this. And here's the other side, but now you have two screens. One here. So this is a screen. Oops. This is a screen. This is a screen. So then you have a photon source here. Light comes out. The beam splitter will deflect half the photons one way, allow half the photons to pass this way, and they come back. So what do you see on these two screens? This one here and this one there. These two screens. What is it you're seeing? Do you see interference patterns there? Do you see no interference pattern? Or do you see black light that can only be seen in the dark? And drum roll please, answer is no interference patterns. That's because the path of each photon, which path information can be found for each photon just by noting which direction it was going as it left the rectangular apparatus. So for instance, all the photons that go this way, then they bounce off this one and they go this way, they all end up here. So we know which path they took through this apparatus. The ones that go here, they bounce off this and they end up on this screen. So we know you get spots on both screens. If your beam splitter is tuned correctly, then you get spots of half the light goes here and half the light goes there. And everybody's happy and you know which one went which path. All the light here bounced off here, came through there. All right? So let's go to the next one. And say, once again, suppose the light is directed toward the beam splitter so the light can either take two paths. However, now a second beam splitter is placed in the opposite corner of the rectangle from the original beam splitter, allowing half light to proceed horizontally and half vertically. So I'm going to switch colors here. And we're going to put the other beam splitter here. BS 2 for other beam splitter. Now, when you see something on this screen here, now it could have come from the lower path because it just went through, or it could have come from the upper path and been deflected that way. Same thing here. So now I've made the, actually I should have put it in the other direction, shouldn't I have? Is there an eraser here? Well, you get the idea. Let's see, can I undo? So actually this one I think should be situated like this. So it can reflect light there or transmit light there. So this is beam splitter 2. What do you see? What do the two image screens show? Do they show interference patterns? Do they show no interference patterns? Does one screen show a bright spot and the other shows nothing? Or do the photons get confused and ask directions? Now they can go either way. Drum roll, please. Answer is 2 answers here. Interference patterns, and one screen shows a bright spot and the other nothing, if you tune it right. So the second beam splitter makes it so that which path information is erased. This is a little bit like the quantum eraser. So each photon that strikes either image screen could have arrived taking either path. Before you knew, but now you don't know. And if you don't know, you get an interference pattern. But you can tune this so that one of the screens has always constructive interference and the other screen has always destructive interference. And if you do that, then one of these, say this one, lights up. And this one has nothing. But it's interference that caused that. So you could stand in the middle here, having a good time. Light could go around you, and it depends whether a second beam splitter is placed there as to whether photons take both paths around the actually called Mach-Zehnder interferometer or not. They take both light paths or one, depending on whether you put this beam splitter there later. Okay, how am I doing on time? All right, good. Poof. So this Mach-Zehnder interferometer, so here's an actual real drawing of it, is shown here, can actually be used to probe whether a sample is placed in the light path. With no sample in the light path, only one of the detectors down here will detect light. Detector 1 could see only constructive interference, and detector 2 could see only destructive interference. So with a sample, each detector has a 50% chance of detecting the photon. Where the sample affects the photon, however, and allows which path information if there is a sample. So now you can tell if there's a sample in the interferometer or not. So you must assume that the sample is otherwise transparent. So for instance, if you put, going back previously, if you put a horizontal polarizer here, then you would be able to tell the photons going around. There, once you can tell the photons, they can't take both paths, because once they hit the detectors, then you would know which ones were which. So once you have a horizontal polarizer there, then you get 50% of the photons here, and 50% of the photons there. If you take the polarizer away, then they constructively interfere. They take both paths again, and you get, let's say, 100% here and 0% there. Okay, so this can be used to test for bombs. I am not making this up. And the people who thought of this are Elitzur and Weidman, and they were going to come up with a way of using the Mach-Zehnder interferometer to test for bombs without exploding them. This sounds like something out of Monty Python, so here we go. A bomb is placed in a Mach-Zehnder interferometer, just like we promised, right here. Let's make it blue. I like blue. The bomb is designed to be light sensitive, so it has to be a special kind of bomb. If illuminated, it will explode. Say, oh, there's a bomb. Boom. The bomb might be a dud, though, and if so, it will just let the light pass. It will be transparent, completely transparent. So a photon is released by A. So here's A here. So what happens if the bomb is a dud? So you got a bad bomb. You put it in your Mach-Zehnder interferometer, which is now an Elitzur-Weidman bomb tester. What's going to happen? Does light take both paths, interferes, and a detector lights up? Does light take the top path if the bomb is a dud, and detector D lights up? So D is this one down there. Is this one. Does light take the bottom path and detector C lights up? Or are both Mach and Zehnder arrested for illicit activities? And the answer would be 1. Light takes both paths for the dud, and a detector lights up. Since the bomb is a dud, it does not affect the light path, a precondition of the experiment, and the interferometer acts as if there is no obstruction at all. Therefore, photons take both the top and the bottom paths, and even if somebody is standing inside the interferometer right here, even if somebody is standing there, they can take both paths. and either C or D will detect the photon depending on which one gets the constructive interference and which one gets the destructive one. Okay, so continuing on. A bomb is placed again in the Mach-Zehnder difframeter. This bomb is supposed to be light sensitive and it's alive. If illuminated, it will explode. The bomb might be a dud though, and so it will just it might just let the light pass. Okay, so we're asking actually here, what if the bomb is real and primed? Will light from A is still the same. It's releasing photons just like it did before. Will light take both paths and will a detector light up? Will the light take the bottom path and the bomb will explode? Will light take the top path and detector D light up and the bomb does not explode? Or hilarity will ensue when the butler throws the whole thing in the trash? It's like a sitcom. And the answer is, think about that. Light takes the bottom path and the bomb explodes. Or light takes the top path and detector D lights up and the bomb does not explode. But it can't take both paths. Once you put a live bomb in there, it has to take one path or the other. It can no longer take both paths. So half the time the bomb explodes, but half the time it does not. Therefore, if detector C lights up, the bomb is a dud. If detector D lights up, either the bomb is a dud or the bomb is live. So if D lights up, you know with only 50% certainty that the bomb is alive. Still, that's better than not detonating it. I mean. So what do we learn? There is no classical way, without quantum mechanics, of determining if the bomb is live without exploding it. However, there is a quantum way, using quantum logic, trying to allow photons to take both paths sometimes. 50% of the time, you will find out that there is a live bomb. So if D lights up, you know one of two things is true. The bomb's either a dud and light took both paths, or the bomb's live and it took the upper path, and you weren't unlucky enough for it to take the lower path. And in that 50% of the time when it took the upper path, you know that you have a live bomb. So this is another example of counterfactual definiteness, determining something definite with quantum mechanics without actually measuring it. So I will leave that here. So this is a case of quantum logic. And I ask you to think about this some more because it's really cool. And next lecture about the lab version of the quantum eraser is also really cool, even stranger than this. And I'll ask you, please keep Schrodinger away from your cat. Same photon. Or can you? Let's go to the quizzing. Suppose a light is directed toward a beam splitter so that light can take either of two paths around the rectangle. Okay, so what rectangle is there? So here we go. Light comes in here, and here's a beam splitter. BS means beam splitter, got it? So then light can go here. I should wiggle it to be a photon. Or it can go up here. A common thing that's going to be occurring in the next two lectures, a beam splitter. So let's say you have light that comes in here, and here is your beam splitter here, which is like essentially a half-silvered mirror that runs like that. So when that happens, two things can happen to your photon. It can come out here, or it could come out here. And if you tune it just right, and it might Welcome to quantum splitting. This is a pretty crazy one, so if you've picked this one out of the list, you might want to stay for the lecture. It's really fun and strange. So this might be tuned by the energy or wavelength of the photon. You can get it so that 50% of the time it comes down here, and 50% of the time it just continues straight. So these are pretty interesting. One of the reasons why it's so interesting is because these paths, these separate paths, can actually interfere. So it's a little bit like creating a two-slit experiment. The beam splitter, you can have photons that can go through the beam splitter and be reflected by the beam splitter both. Physics X, Extraordinary Concepts in Physics. I'm Robert Nemiroff, who's teaching this in the beautiful downtown studios of Michigan Technological University. There are students taking this class, but you can, if you can discern this web address here, right there, you can, oops, make it stay, you can see all the lectures of this class. So let's get started here. First, I need to define